Well, first thing is next week there are no labs. Because of MEA. And there's also no Thursday class, but this class I'll still do. And then I'll put a video up of it and everything. So if you can't make it or something, the video will be there. And I still owe you your first lab exams. I'll get that done before, well, hopefully by the end of this weekend. Okay, so so far in this class, we've been talking about kinematics. And kinematics mean that all you're doing is describing motions. I would say it's very likely that on a future quiz, I'll ask again something about what kinematics means, what kinetics means the next thing. A lot of people got it wrong last time. But kinematics is just describing the motion, not talking at all about the causes of motion. Okay, it's just information that you could read off a video, for example. Okay, you can't tell how hard two things bump together on a video, but you can measure how fast they bounce off of each other. That's kinematics. Okay. Now we're going to get into kinetics. And kinetics combines kinematics with the causes. And kinetics and kinematics both have like Greek roots, I assume, maybe Latin roots, but there's no doubt that it's confusing that they sound so much alike. Like that is not helpful to have those two words sound so much alike. But the shorter word is the more complicated thing, and the longer word is the simpler thing. So now we're going to take what we've learned so far and combine it with trying to figure out what causes this motion and how the causes relate to the motion that happens. The main equation for kinetics is going to be Newton's second law. And Newton's second law says if you add up all the forces acting on a body, that's equal to the mass of the body times the acceleration of its center of mass, or sort of the acceleration of its center. So this is all the forces acting, bless you, on the chosen body. M is the mass of the chosen body. And A is the acceleration of the chosen body's center of mass. You can see that the idea of being very clear about the chosen body that you're dealing with is going to be an issue, and we're going to talk about that starting with free body diagrams. But before we get to using Newton's second law, before we get to using this key equation from kinetics, and I would say the most important equation in this whole class is Newton's second law, we have to define the things that go into it. We already know what acceleration is, but we haven't talked about forces yet, and we haven't talked about mass. So before we can use this equation, we need to define mass and force. By the way, there's also an important Newton's first law that we'll do a lab about, and an important Newton's third law that we'll use quite a bit. But this is the one that really everything is keyed off of. Okay, so first I'll define mass. And mass is a measure of an object's resistance to acceleration. Okay, so if something has a very high mass, it's hard to make it accelerate. If it has a very small mass, it's easy to make it accelerate. So for example, I don't want to make this like gruesome or anything, but think about like cars running into each other. Think about it at a slow speed so it's more peaceful. But like imagine you have a pickup truck, okay? And it's going, 15 miles an hour. And it runs into like a little tiny compact car that's going 15 miles an hour. Okay. What's going to happen? That pickup truck is going to slow down when they collide, but the little car is going to end up moving in the opposite direction that it was going. One way to say that is that before the collision, the compact car has a velocity that's going to the, what direction? Left at 15 miles an hour, right? And then very quickly as the collision happens, that velocity changes, right? So the car's velocity changes quickly. And if a velocity changes quickly, that means there's a large acceleration. And the pickup's velocity doesn't change much compared to the car, at least. So that's a small acceleration. But now imagine what happens if you have the exact same pickup truck going the exact same speed, and it collides with, you know, a semi-truck kind of thing. That's coming the other way. Now the relationship when they collide is reversed, right? The pickup truck is going to have a large acceleration, and the semi is going to have a small acceleration. Well, in the two examples, it's the same pickup truck, so it's not anything it's doing differently. The thing that matters is just what it's running into. Is it running into something that resists acceleration a lot or resists acceleration a little? Okay. The compact car has a very low resistance to acceleration. This same pickup truck can make it accelerate a lot. The semi has a large resistance to acceleration. The pickup truck doesn't make it accelerate much at all. Okay, so that's the idea of mass. The SI units of mass are kilograms. So that's the unit we're going to pretty much use all the time. You might think grams because it doesn't have a prefix, but this is just what it is. One thing to notice about the mass, and so before I write this, you could actually like measure the acceleration, measure the mass of things by using some uniform, you know, like quantifiable thing to try to make them accelerate and seeing how much they accelerate. You know, that thing is a force. We haven't talked about that yet. But based on how much something accelerates, you could come up with a number that defines its mass. Okay, that's what mass is. I know, like, we're sort of more used to thinking of mass in relation to weight, you know, and your scale has a setting that converts from pounds to kilograms. But really what mass is just how much you accelerate with some kind of given impulse applied. And we'll get to the relationship between mass and weight pretty soon. Okay. So notice that mass is always a positive number. And it doesn't have a direction. So it's not going to be a vector. So what happens if you multiply a positive number to a vector? And I'll talk in a second about why that's going to matter to us. But we know that mass is going to be a positive number. Remember what happens if you multiply a positive number to a vector? That's right. And what happens to the direction of the vector? The direction stays exactly the same. Okay? So remember, if you multiply a positive number to a vector, you get a vector in the same direction. The only thing that changes is it's a different length, a different magnitude. Okay, why does it matter what happens when you multiply a positive number to a vector? Because if you look at Newton's second law, which we're heading towards, we're multiplying the mass, that positive number, times an acceleration vector, okay, to get another vector. And so what this tells us is that the sum of all the forces, this net force acting on an object, is always going to be in the same direction as the acceleration of the object. Okay. So therefore, Newton's second law, I'll always abbreviate that N2L, Newton's second law, says, well, the acceleration vector and the net force vector will always be in the same direction. Can you multiply a positive number to a vector and get 0? Only if you multiply by 0, right. So that's exactly right. And we're not going to be dealing with any objects with 0 mass. And so what that means is, if you look at this equation, if you look at the motion of an object and there's no acceleration, meaning it's constant velocity, there can't be any net force on the object. Okay. The only way you can have a net force on an object is if there's a non-zero acceleration vector. Okay. Okay, so that's about it for mass. So now we have to think about force, and that's a little more complicated because it does have direction. So force is a vector that measures the intensity and the direction of a push or a pull. The units of force are, well, the units just come from Newton's second law. So what are the SI units for acceleration? Meters per second squared. And I just said that the SI units for mass are kilograms. So the SI units for force are kilogram meters per second squared. That's pretty cumbersome to work with, so we're going to give that its own name. But it's, so in general, it's units of mass times length divided by time squared. And in SI units, that means that it's kilogram meters per second squared. And because we're going to use this a lot, and that's a painful unit to work with, we're going to give this the name Newton, after Isaac Newton. And we'll abbreviate it as a capital N. In this class, the forces applied to objects have to be, there's only two categories for the kinds of forces that we're going to see. So let's see, forces applied to objects fit into two categories. And keeping that in mind is going to make it easier to figure out what all the forces are on a body, because you just have to make sure you're dealing with these things. The first one is the weight. And this is where we get into the distinction between how we're used to thinking about mass and what mass really is. We tend to think of, I think really just because of the bathroom scale thing, we tend to think of mass and weight as the same thing. But mass just has to do with how easy it is to accelerate something. Weight is the force that gravity applies to your body. To any body, So this is the force applied to a body by gravity. And then there's only one other way that a force can be applied to an object, and that's through contact with its boundary. So contact with another body at the boundary. There are some other ways forces can be applied, but we're not going to deal with them in this class. Electric fields, magnetic fields, those can apply forces, but we're not dealing with charge or magnetic fields or anything like that yet. Okay, so this is it. When you're trying to think of the forces that's applied to a body, just think like, okay, what's the weight force? And then look around the boundary and say, like, is there anywhere that there's contact with something else? And once you take care of all those things, you're done. You don't have to worry about it anymore. Okay, any questions about mass or force? All that's sort of philosophical so far, but we're going to get into some calculations now. So now we're going to get into Newton's second law, and we're going to use it to calculate some stuff. So we know that if you take all the forces acting on a body, that's equal to the mass of the body times its acceleration. It's the acceleration specifically of the center of mass, but we're going to keep treating things as particles, which means we're just assuming they only exist at their center of mass anyways. So I'm going to leave that off for now. But remember that this means, you know, at the center of mass. And we're going to use this equation first to try to figure out how much force gravity applies to things. So we're going to use Newton's second law to determine the force gravity applies to objects. This is a vector equation, so I'm going to write it out in its component form, just to be clear for when we go to the calculations. So in component form, you can think of this as Fx, Fy, that's the x and y components of the force, are equal to the mass of the object times the x and y components of the acceleration of the object. And because of the way multiplication by a vector with a number works, you can also think of this as m times the x component of the acceleration, and then m times the y component of the acceleration. Okay, so the first example we're going to think about is a 1 kilogram object. Okay, so you have a 1 kilogram object in free fall. If something's in free fall, how many things are acting on it? Only gravity. And if you think about what's going on around the boundary, the thing isn't on a table or anything. It's in the air, you know, being launched or falling or something. And we're ignoring air resistance when something's in free fall. So the only force is gravity. So we're going to use the free fall case to try to calculate the weight, the force that gravity applies to an object. Okay. Do we know anything about the acceleration of an object when it's in free fall? That's right. So whether it's being launched up or falling down or whatever, the acceleration is down at 9.81. Okay, so if we put the y-axis up, then the acceleration of this thing in free fall is 0, negative 9.81. And so Newton's second law says the force of gravity I'll call it, so the gravitational force x component and the gravitational force y component is equal to the mass, 1 kilogram, times the acceleration, which is 0, negative 9.81 meters per second squared. And if you multiply that through the 1 kilogram to both components, you get 0 for x, and for y, you get negative 9.81. The units are kilogram meters per second squared, or newtons. So what we figured out is that gravity is applying a downward force of 9.81 newtons to this object. Okay. We figured that out using two things. We knew that the only force acting on the thing in free fall was gravity, and we knew what the acceleration was. Okay. So now think about something. This is a little tricky, a little confusing, but think about this for a sec. So in that video that I showed you of where they evacuate that big room and drop the feather and the bowling ball, what we saw is no matter what the mass of two objects is, if there's no air resistance, they fall with the same acceleration, right? And so I said gravity, what we learned is that gravity doesn't make heavier things fall faster, right? So now what do you think the force is going to be if we think about a different object in free fall? So now let's think about a 10 kilogram object in free fall. The acceleration is going to be the same. What do you think we're going to find out about the force that's applied to it by gravity? It is going to be 10 times more. Is that confusing, kind of? So the acceleration is the same. Let's go through the calculation, and then I'll, talk about how this works. Okay, so now we have a 10 kilogram object in free fall. And free fall says the only force is gravity. So these are the components. And that's equal to 10 kilograms times the acceleration vector. And what's the acceleration of this 10 kilogram mass? Yep, that's still exactly the same, 0, negative 9.81. And so if you multiply these together, you get 0 for x and negative 98.1 for y. Units are newtons. So that force is 10 times as big. So how can it be if the force that gravity applies to things depends on the mass? How can it be that gravity doesn't make heavier things fall faster? Well, the answer is, think about this. Go back to this truck example, In order to make that car accelerate a certain amount, the pickup truck had to apply a certain force to it, right? A relatively small force. In order to make the semi-truck accelerate that same amount, that pickup truck would have had to apply a much, much bigger force to it. Okay? So the amount of force that you have to apply to something with more mass to get the same acceleration is bigger. And so that's how this works out. Gravity applies a smaller force to a smaller thing and a bigger force to a bigger thing. And those forces that it applies are just the forces required to make a smaller or bigger thing accelerate down with the same acceleration. Okay. Anybody have any questions about that? I feel like I could have worded that a little better, but
explanation of mass, a measure of an object's resistance to acceleration, explains it below.
Yeah.
Because more mass it has, the more resistance.
Exactly.
It's going to take more force.
Exactly. Yep. Exactly. And so now that we figured, okay, so what this tells us is, so let's do it now for a general mass and see what the force is. So now let's say an object with a mass m, okay? And again, this is in free fall. So now Newton's second law says the x and y components of the gravitational force is equal to m times 0, negative 9.81 meters per second squared. And so that's equal to 0 for x and negative 9.81 newtons for y. And you can also write this as 0, negative m lowercase g if you define this lowercase g as positive 9.81 meters per second squared. So that's the force that gravity applies. What do you think, like intuitively, what do you think happens to the force gravity applies to things when they're falling versus on the ground versus being pushed up into the air? Anyone have opinions on that? It is always the same. I'm not sure. Yeah, I'm not sure if that's everybody's intuition, but you're just going to have to accept that. I don't have like a proof for that. But the force that gravity is applying to this thing in free fall is the same as the same force gravity is applying to it if it's resting on the ground. It's the same force gravity is applying to it if you're doing something with it. So no matter what an object is doing, gravity applies a weight force of mg down to the object. Okay, so now we figured that out. Let's think about what happens with a bathroom scale and get a sort of a relationship between the mass and the weight that you measure on a scale. Or rather than measure, let's say we're going to calculate the force applied to a person by a bathroom scale. Okay, so here's the setup now. You have a scale on the floor and a person on the scale. This person isn't super psyched to be weighed in front of everybody here, but that's how it is. Okay. Let's say that this person has a mass of 80 kilograms. Okay, so we want to calculate the force vector that's applied to the person by the bathroom scale. So what are the forces applied to this person? Gravity, yep. So the forces are the weight. That's the force applied by gravity. And there's only one other one, the force applied to his feet by the bathroom scale. We know that's the only other one because that's the only thing touching the person's boundary, you know? There's nothing else touching the hands or the head or anything like that. So Newton's second law says, well, the weight force, what's the weight force for this person? It's 0, negative 80 times 9.81. Plus the force from the scale. We don't know what that is, but we're going to calculate it. So let's call that Fx and Fy. Is equal to the person's mass times the person's acceleration. What's the acceleration of a person standing on the ground? 0. And so you get that well, so with any vector equation, you can do it component by component, or you can do it as a full vector equation. I'm going to break this up into components and do the x component equation first and then the y component equation. So you can think of this as 0 plus fx is equal to 80 times 0. Solve that algebra and you get that fx is equal to 0. So the bathroom scale isn't applying any x component of force to the person. And then the y component says negative 80 times 9.81. So that's negative 784.8 plus Fy is equal to 80 times 0. And so Fy is equal to positive 784.8 newtons. So put these together and you get that F is equal to 0 for X, positive 784.8 for Y. If a vector has no X component and a positive Y component, what direction is it pointing? Up, yep. So remember, you can think of that as like a vector is the same thing as if you put a tail of a vector at the origin, its components are the coordinates of the head, okay? So imagine the tail at the origin, the coordinates of the head are 0, 784. That's an upward vector. So this is a force vector pointing up with a magnitude of 784.8. And so that's the way a scale works. It measures the force it's applying to your feet. And that force that it applies to your feet is equal and opposite to the force gravity is applying down to you. If you're not touching anything else, you know. Any questions about that? Yep. You know what, where Newton's third law does come into this problem? It's not exactly Newton's third law, but it does come into it because the scale can't measure the force that it applies to the person. It can only apply the force the person applies to it. But then Newton's third law says those are equal and opposite. But we'll get to that pretty soon. Any other questions? And so how does a scale, so a scale measures a force, not a mass, okay? But how does a scale tell you what your mass is in kilograms? Well, a scale assumes that you're taking your measurement somewhere on the surface of the earth, you know? And so it electronically, or just by the way the dial is set, divides G out of whatever weight is measured. And what you're left with is the mass. And so it says, okay, if you're using this scale on the surface of the earth, where things in free fall accelerate down at 9.81, then your mass has to be this. But it's not really measuring your mass, it's measuring the force gravity applies. So if you went to the moon with a bathroom scale, you know, and measured yourself, because gravity is a lot weaker there, the scale would measure a much smaller force. It would still be assuming that you're on the surface of the earth, so it would tell you a mass that's wrong. You know, your mass doesn't change when you go to the surface of the moon, but a bathroom scale would say that, would estimate that your mass was way less than it is. It's actually really important for astronauts to know what their masses are doing when they're in space, because you can lose apparently a lot of muscle and bone density, like when you're in a space station or whatever. So they have to measure their mass all the time. And if you're in a weightless environment, you can't use a bathroom scale, because what it's really measuring is the force gravity applies. And if there's gravity isn't applying a force, you can't do it. So what they do is they actually measure directly your resistance to acceleration. Apparently, I've never seen this thing, but apparently it's like a contraption that just like jiggles you, and it knows the forces that it's applying as it jiggles you, and it's measuring your accelerations that go along with those forces. And so if you're easier to accelerate, it measures that your mass is going down. And if you're harder to accelerate, it measures that your mass is going up. Okay, let's do another one, because I can tell how much everybody likes these calculations. So we'll do some more. I wasn't going to, but I can tell you really want to. Okay, so now let's do, let's put a bathroom scale on an elevator. Well, when, so an elevator, most of the time you're riding in an elevator, the velocity is basically constant, you know. But right at the beginning, when you go from rest up to whatever speed it's going, there's an acceleration because the velocity is changing over some time, you know. And so if you're going from rest to moving upwards, it's an upwards acceleration. And if you're going from rest to moving downwards, it's a downwards acceleration. So let's see what a bathroom scale would read during an upward acceleration or a downward acceleration. Okay. So first, let's say that the elevator is accelerating up at 2 meters per second squared. What's the force, you know, that the scale applies to the person, or, you know, which is just the force that the scale reading gives you. So what's the force applied to the person by the elevator? Okay, so Newton's second law says add up all the forces acting on the person. What are the forces acting on this person? Yeah, so it's still just this, and there's still the scale between the person and the elevator, so it's still just the force, the scale applies to the person, and the force of gravity. So the weight is 0, negative 784.8. And we want to measure the force applied by the scale. That's what the reading is going to be. And that's equal to the person's mass times the acceleration. What's the acceleration vector? Yep, it's up at 2 meters per second squared, so it's going to be a 0x component and a positive 2y component. So if you break this up into the two separate equations, you get 0 plus fx is equal to 80 times 0. Or in other words, fx is equal to 0. And negative 784.8 plus fy is equal to 80 times the y component of the acceleration, which is 2. And so now solve for fy, and you get 944, is that right? 944.8. So the total force vector applied to the person by the scale is 0, positive 944.8. Or you can think of that, you know, that's a positive y and 0x, so that's an upward force of 944.8 newtons. So in this case, during that brief period of upward acceleration, the scale actually tells you that, it reads a value that's bigger than the force gravity applies to you. It's bigger than your weight. So in this sort of, if you try to use a scale while you're accelerating, it's not doing what it's intended to do. It's not telling you what the force of gravity is. Okay. What do you think is going to happen if the scale's accelerating, the elevator's accelerating down? What? That's right. That's right. So I'll do that quickly, but what we're going to see is that if it's accelerating downward, the scale reads a smaller value than the weight. Okay. So now let's say the elevator accelerates down at 2 meters per second squared. Then Newton's second law, well, the forces are still the same. There's still just the weight force, and then there's any force from contact with the boundary, and that's only at the scale. So we have 0, negative 784.8, plus Fx, Fy, and that's equal to 80 times the acceleration, which is 0, this time negative 2. The x equation says 0 plus Fx is equal to 80 times 0. So Fx is equal to 0. And the y equation says negative 784.8 plus Fy is equal to 80 times negative 2. And so Fy is equal to, I think that's 624.8. So if you put those two components back in the vector form, you get that the force is equal to 0, 624.8, or an upward force of 624.8. Any questions about that? All right, well, with these examples, the way we approached it was we said we don't know anything about the force applied to the feet by the scale, and we were able to calculate that because we knew enough other stuff. But there are going to be cases where, pretty much every case, where we're going to need to know something about the direction of the force that things apply. And so that's the next thing we're going to get into. I'm not going to do that today, but that's the next set of videos you're going to get is going to be on that. So like the next subject, the next topic is the direction of specific kinds of contact forces. And the ones we're going to see are pulling forces. You can think of those as forces that can be applied by like a rope or a cable. Pushing forces. The force applied by the scale is a pushing force, but we just didn't have to know anything for this particular problem about the direction. But we'll learn more about that. And then the third one is friction forces. The next videos I'm going to give you, videos, like assigned videos that go over this same stuff that I talked about here. It uses some different examples and stuff, but it's basically the same topic. So if you feel pretty good about this after listening today, you can sort of skim through that and not worry about it too much. You might want to just glance at the notes, or if it was sort of confusing, maybe those videos would help you. But just so you know, this same information is sort of coming at you again. And so just use it as much as you want, as much as you feel like you need. But then this is the next big thing, the next new thing that we're going to get into is how to treat these individual specific force types. Anybody have any questions? Yeah. Oh, yeah. Oh, yeah, there's no 10 or 11. Or there's a 10, but no 11. 9 and 10, yeah. Yeah, okay, I'll change that. Someone else mentioned that too, and I forgot. Any other questions? Okay, that's all for today. So don't come to lab next week.